All right, welcome back. So it's been a couple of days of working on optimization, so using calculus to do some contextual problems. Here's a different type of problem. It's called a related rates problem. And so the gist of these types of problems is that there are sort of measurements or things we're interested in that can be represented with numbers that are changing as time goes on. And so the thing we're going to be really focused in on is that we don't really want time to be an explicit variable in our setups. We want it to be an implicit variable. And I'm using the word implicit deliberately because that's going to tell us how we need to differentiate. So we're going to use differentiation to help us out here. So let's take a look at a problem here that I've already sort of started setting up for us. So a water tank has the shape of an inverted cone with a base radius of 2 meters and a height of 4 meters. If the water is being pumped into the tank at a rate of 2 meters cubed per minute, find the rate at which the water level is rising when the water is 3 meters deep. So I've started the notice step here. So notice I'm starting with my diagram. So I have here my inverted cone. So the green is my tank. I drew some water in there. And then I have labeled the side lengths. Okay, I've labeled them with numbers because the tank is not changing size at all during this problem. Another thing that's not changing is the rate at which the water is being pumped into it. Things that are changing though, well, if we're pumping water into this, the water is going to be changing. The volume of the water level, the radius of the water, those are all things that will be changing. So because of that, I don't want to slap down right now 3 as the height of the water because it is not 3 always. We're interested in what's happening at 3, but this is a motion, like a moving problem here. So maybe the water started down here, it fills, and then we're going to be interested in when it's at 3. So because it's changing, I don't want to label it with numbers, I want to label it with variables. So I will choose sort of the more natural sort of variables here, R being the radius of the water and H being the height of the water. Okay, so at this point, maybe this is all I notice. So now I'm going to go ahead and move on to my links. So links. Well, I definitely know that volume is a part of this because the volume is changing for the water. So how does volume get represented? Volume is, oh boy, so a cone. Maybe I have to look this up. Maybe you just remember it. I think it's 1/3 pi r squared times h. Yeah, that sounds right. So like this, without the third, that's a cylinder. So the base area, pi r squared, times how tall it is. But then it's just 1/3 of that, which actually we might be able to prove next unit, or not next unit, next week, I don't know, I can't remember what the schedule is, but in the next couple weeks we'll be proving some volume stuff. Okay, so then at this point I might be like, cool, I'm not so happy about all of these different variables. 2 variables, that would be fine, like that's what I'm used to, but 3 different variables is not looking so good. I could move forward, but it's not. I'm not going to be happy with that. So here's my next goal: is I want to try to figure out, can I relate R and H to each other in some sort of way? So this is where I need to go back to my noticing phase. So my noticing phase has restarted, and I come back up and go, okay, so R and H. Can I figure out how they are related to each other? And maybe you don't see this immediately, but hopefully once I do it, you do start to see it. If I just draw in this, what I see now are 2 different triangles. We've got the triangle whose height, it's a right triangle, whose height is 4 and its base is 2, or other leg is 2. And then there's this one here. Oh boy, I drew that horribly, but we'll go with it. Whose length there is R, and that length is H. And we know that these angles here are congruent because, well, they share that one here. It's sort of like nested triangles, I think is the name. So what does this mean? Oh, well, this means that we have similar triangles. Yay! Okay, so I can create a relationship with R and H in it and see if I can try to solve for one versus the other. Okay, so let's do that. So I'm going to come back down here to my links, and based off of that new notice, I'm going to write down, oh, so 2 over 4 is going to be equal to R over H. They're proportional to each other. This means that I can solve for R or for H and try to come up with a representation here. I think I'm going to solve for R, which means I'm going to come over here in a moment and replace R. The reason I'm doing that is because if I look back at the question being asked, it's about how much is the water level rising by. That's talking about the height. So if I can keep height in my equation, that means it's going to be a little bit easier to answer this question more quickly, more directly. It's still possible if you solve for H, but you're just going to have to do a little more work. Cool, so I want to isolate R, which means I need to multiply both sides by H, which will get me a half H. I'm going to reduce that 2/4 as well. Cool. Okay, so with that in mind, that means that I can now substitute this into this. So we got volume equals 1/3 pi times, not radius, we're not going to plug that in, we're going to plug in a half H squared. And let's simplify that before we move on. So if we square the half and then multiply it by 1/3, we're going to get 1/12 pi. And then there's going to be h to the 3rd power. Great. Okay, I like this a lot better. I only have v and I have h, 2 variables. That's nicer. If I can sort of shrink down the number of variables, that's always going to be nice. Okay, so now let's go ahead and continue onward here. So in this problem, everything is changing with respect to time. So I need to figure out how the quantities are changing as time goes on. So I'm going to write down my original relationship here. So 1/12 pi h cubed. Okay. And so what I'm going to do now is I'm going to differentiate both sides of this. Not with respect to h, though, because I actually don't know how h is changing. That's actually what my goal is. What I'm going to do is I'm going to differentiate it with respect to time. So we'll call time t. So I'm going to differentiate with respect to t, which kind of makes sense because if you look at our units here, we got meters cubed per minute. We need to somehow get that into play. Volume is in meters cubed. Time is in minutes, so we're about to get that quantity here. So we got v prime. Boo! Okay. Or dv over dt if you wanted to. 1/12 pi is a constant multiple. Bring it along for the ride. Great, and now we're going to take the derivative of h cubed. So here we're taking the derivative with respect to time. So this is like thinking about like something cubed. Well, the derivative of something cubed is 3 times the something squared. But since that something is not t, we need to use implicit differentiation. So we'll multiply by the derivative of that variable. Technically, the same thing happened over here. Like you take the derivative of something, well, it's just 1, and then times the derivative of that thing. But that's not as important to sort of notice. All right. So now we need to start throwing in, actually, let's simplify this. So this will be v prime equals, if we multiply by 3, that'll change this to a 4th pi, h squared h prime. Okay. So there's a couple of maneuvers we can do now. The goal of this problem was to figure out how height is changing, which I now have that variable, h prime, so I could solve for that. You could also plug in stuff if you wanted to. I think I'm gonna plug in stuff. That's what I feel like I want to do right now. So let's start thinking about what we can substitute in for our different stuff. hopefully, fingers crossed, we can substitute in stuff for V prime and H. And the only thing we don't know is H prime, because the question is, how is height changing? That is H prime. So let's make sure that we can substitute those things in. If for some reason I'm lacking one of those pieces of info, I need to go back to my notice phase and maybe return then to my links phase to work through that. Okay, so let's see. V prime, how is the volume changing? Let's look back up in our information. We have that right here. Water's being pumped into the tank. That's changing the volume. That is a volumes unit right there. That is the rate of the volume. So we know that it's 2. It's going into the tank, so it's increasing by 2. That's a positive 2. All right, let's keep going. 1/4 pi times h squared. Do I know the height? Well, let's come back up. We do know the height. The moment we're interested in is when the height is 3 meters. So we can come back down here and substitute in 3. Great. So now let's simplify and solve for h prime. So we get that 2 is equal to 9 pi over 4 times h prime. So multiply both sides by 4 to get us this, and then divide by 9 pi to get us that quantity. All right, and so now let's answer the question in the problem here. So find the rate at which the water level is rising. So the water level is rising by 8 over 9 pi. Let's think about our units. Height is being measured in meters. This is a rate. So per some time frame, minutes is the one we're using in the problem. When the water is 3 meters deep. And there you have it. So let's do a quick recap. All right, so start with your noticing. So remember, I didn't notice this at first. I just had this diagram. That purple line was not in there. Okay, so I came down here and I came up with this. And then I was like, that's a lot of variables. I wonder if I could maybe shrink down the number of variables. So then I came back and noticed I had similar triangles, wrote this relationship, and did this substitution. So always think about that. You might have to return to your notice phase. Okay. And then we differentiated with respect to time. Notice that time is not in our equation at all, but we are differentiating since every single thing is changing as time goes on. So we use implicit differentiation to get this. And then we substitute in the values we do know. We knew that the volume was changing by this much. We knew that the height was going to be 3 when we're interested. And so we just had to solve for h prime, which we did, and we interpret it this way. So we're going to do a lot more of these types of problems. So not all of them will be volume problems. Sometimes they're surface area. Sometimes they're Pythagorean theorems. Sometimes I'm blanking on what other ones there are. But we'll do some more in class, right? And we'll be able to ask lots of questions during that time. So come prepared, ask lots of questions. And please take the survey so I know what questions you already have before you walk in. Thanks.